Okay, so we discussed at Fleming's left-hand rule and the effects like the force on a current carrying conductor yesterday. Today we will talk about the DC motor. It is easier compared to the AC motor, and then they're going to talk about some practical scenarios where DC motors are used. After that, we will talk about very briefly the moving coil galvanometer and then transformers, right? So we'll spend a bit of time on that, and hopefully by the end of this session, we will actually be done with unit 4, right? So let's get started now. For the DC motor, right, the explanation is given over here, how it works, a simple DC motor, but I will take the aid of a video, so let's take a look at that. Okay, let me just put that up on screen for you guys. Can you see that?
Yep.
Okay, let's get started. Now I put that at 1.25 playback speed. Hopefully it's not too fast.
Although AC motors are the most common type of motor used in industry, direct current or DC motors are also used. One common use for a DC motor is as a backup motor for a critical process. DC motors can run on the direct current supplied by a battery when there is a failure in the alternating current supplied to an AC motor. For example, this DC
Right, so we know that the current being supplied from the main power grid, right, is alternating current. And so, right, the backup batteries that we have, like a UPS or something, or like a solar, that is DC. Okay.
Yes.
Okay.
motor is used with a backup pump that supplies oil to the bearings in a large piece of equipment. Normally, an AC motor drives a separate pump that supplies oil to the bearings. But if that motor fails, the DC motor-driven pump can be used to provide the oil. This is an illustration of a DC motor. In this simplified example, the stator consists of two permanent magnets. The rotating part, which is shown as a loop of wire, is called the armature. The armature
And this is actually like a coil. Okay, and what they're going to talk about over here is the application of Fleming's left-hand rule, right? So when there's current through a conductor in a magnetic field, a force, the wire will experience a force and it will be moved. And so that's what they're going to talk about.
is connected to a source of DC power. These two components are called brushes. The brushes are connected to a DC power source. A conducting ring, known as a commutator, is mounted on the end of the armature. The commutator is not a solid ring. It consists of conducting segments that are separated from each other. During operation, the commutator makes sliding contact with the brushes. Current flows from the negative side of the DC power source through one brush to a commutator segment. The current then flows through the armature in this direction, back through the other commutator segment to the other brush, and to the positive side of the power source. The poles are perpendicular to the armature. So when current is supplied to the armature, motor action is produced. The interaction between the stator's magnetic field and the armature's magnetic field causes the armature to rotate. Even though the armature has turned, the current still flows from the negative side of the power source through the armature to the positive side of the power source. However, the commutator has physically changed the direction in which the current flows through the armature. This change in direction changes the polarity of the magnetic field created by the armature. So the brushes and the commutator in a DC motor enable the armature to change its magnetic field, and as a result, the armature turns continuously. The example we use to
Okay, now if any of that made sense, let's take a look at the book and the explanation. Hopefully it will be easier to digest. Right, and so a rectangular coil of wire mounted on an axle which can rotate between the poles of a magnet, may experience a turning effect when a direct current is passed through it, right? So that is what the DC motor is. The turning effect increases if the number of turns of the coil increases, if the current flowing increases, or if the strength of the magnet increases, the magnetic field. Now what's happening over here is, if you use Fleming's left hand rule, right? If you need, I'll turn on my camera, otherwise, use your hand the way we learned yesterday for Fleming's left hand rule. And so your forefinger is going to be in the direction of the magnetic field, which is north to south, right? So it's going to be pointing from left to right. And you can see that in arm AB, the current is flowing from top to bottom. So your second finger is going to be pointing towards yourself. And if you place your hand that way, your thumb will be pointing upwards. And so, right, when current is flowing through the wire this way, right, side AB is going to experience a force upward. And if you do the same thing for side DC, right, it's going to experience a force downwards, right? So you just like flip your hand the other way. The magnetic field is still from left to right. The current is flowing from bottom to top. So the second finger is pointing away from you. And now your thumb is pointing downwards. Are you following that? Are you using Fleming's left hand rule?
Sir, is it okay if you show us the visual
All right.
representation?
Yeah. So let me just switch on my camera. Okay. And over here, right. So as you can see, right, the magnetic field is going from so it's going from
Yeah.
north to south, right? It's going from left to right. And the current in arm AB is going from top to bottom. So your second finger is going to be pointing towards you.
Yeah,
And so with
yourself.
that, and so with that, the thumb is pointing upwards,
Yeah.
right? And so in the arm AB, there'll be an upwards force, and so arm AB will move upwards,
Yeah.
right? For CD, right, the magnetic force is still the same way, but the current is going in the opposite direction, right? The current is going from bottom
Yeah.
to top, right?
Yeah.
And so you just flip your hand north to south, so that's the magnetic field. Current going up, so right away from you, the second finger, and so the thumb is pointing downwards,
Yeah.
right? And so in CD, there'll be a downward force. And so what will happen is it will make like a half rotation and it will become vertical. Right now, the coil is horizontal. It will become vertical. Now, it
Yes.
won't stop at being vertical, right? It will sort of overshoot slightly. So it will be slightly diagonal, leaning towards the right. Now, what happens is, right, when it turns, the connection reverses, right? It mentions over here, if I just focus on the book, it mentions over here that the brushes are then in line with the gaps of the commutator and the current stops. However, because of inertia, so remember inertia from way back in unit 1, the coil overshoots the vertical and the commutators have change contact from one brush to the other, right? So it slips. And so this semicircle ring, the commutator, is also rotating. So now it was initially in contact with the positive terminal. It switches and now it's the one on the right is now on the left and it's in contact with the negative terminal. The one that was on the left turns and is now in contact with the positive terminal. And so what that does is that it reverses the flow of current, right? And when it
Yeah.
reverses the flow of current, now you have an opposite force. So initially, what you were having is, right, for the AB, right, you were having an upward force, but now, sorry, yeah, this way. So now the current is reversed for AB, and so now AB is experiencing a downward force and CD is experiencing an upward force, right? Because the flow of the current has reversed.
Yeah.
Are you following?
Yes.
Right? And so with each turn, the current keeps alternating, and so the force experienced by the arm that is on the right side over here, right? Over here on the right side
Yeah.
is a downward force, and the force experienced by the arm that is on the left side near the north pole of the magnet is an upward force. So it keeps rotating in a clockwise direction.
Yeah. Okay.
Okay.
Yes.
All right. So right, just yeah. Now practical motors have certain features. A coil of many turns wound on a soft iron cylinder or core, right? And it which rotates with the coil. This makes it more powerful. So the coil is right, the iron cylinder is rotating with the coil. It makes it more powerful, and the coil and core together are called the armature. Several coils, each in a slot in the core. So you can either have one coil around an iron core, a soft iron cylinder, or you can have several coils, each in a slot in the core, and each having a pair of commutator segments, right? So this supplying the current. This gives increased power, and so you have current being supplied individually, and so that gives it more power and smoother running. The motor of an electric drill is shown over here. So right, you've got these connections over here. And finally, an electromagnet to produce the field in which the armature rotates. So most electric motors used in an industry are induction motors, and they work off AC, like the person in the video said that they normally use AC motors, but right, and they work on a different principle from the DC motor, but the DC motor is kept as a backup or used in certain devices such as the electric drill and stuff. Okay.
Yes. Okay.
Now coming to the moving coil galvanometer. If I just zoom out a bit to have all of that on screen. So a galvanometer detects small currents or small potential differences, often of the order of milliamperes or millivolts, right? So milli is obviously 10 to the power minus 3, right? So 1,000th. In the moving coil pointer type meter, so over here, a coil is pivoted between the poles of a permanent magnet. You can see over here.
Yeah.
Current enters and leaves the coil by hairsprings above and below it. So here and here, right? And you can see the connection to the terminal to whatever power source it is or whatever you're measuring. When there is a current, a turning effect acts on the coil as in an electric motor, right? So Fleming's left-hand rule, causing it to rotate until it is stopped by the springs. The greater the current, the greater the deflection. So right, the more the current, the more the force, obviously, because the magnet is of a particular strength. You're not changing the strength of the magnet, which is shown right. So the more the current, the more the force, and so the pointer will move further. Okay.
Yes.
The soft iron cylinder at the center of the coil is fixed, and along with the concave pole of the magnet, so these things, right, you can see the curved inwards, and if you remember from lenses, when it's curved inwards, it's called concave, right? It produces a radial field, right? So a circular magnetic field. That is, the field lines are directed to and from the center of the cylinder. The scale on the meter is then even or linear. That is, all the divisions are the same, right? So, 0.5, 1, 1.5, 2, 2.5, all the way till 5, and then onwards and onwards. So even divisions. Not complicated, I believe. Pretty simple, straightforward. So
Yeah.
so this is another example of something that's telling you, oh, it's an application of what we've learned. You just need to know how it works. Okay.
Okay.
Then we come to the transformer. So a transformer is a setup which changes an alternating voltage from one value to another. Right? Okay, zoom in.
Yeah.
And that value can be either greater or smaller. So you've got voltage coming in of a certain value, for example, 10, and the setup of a transformer can convert that voltage of 10 to 25, or it can convert it to 5, depending on how it is set up. Okay. So it has a primary coil. So over here in the illustration, you can see that the primary coil is illustrated in red and the secondary coil is illustrated in blue. And there are two different ways in which it can be set up. It has a primary coil and secondary coil consisting of insulation coated wires. So, they have that insulating layer over them. It's not just the metal wire that they're using. Wound on a complete soft iron core, right? So this block over here is a soft iron core, either on top of one another. So you can see over here that you have the secondary, and on top of that you have the primary, or on separate sides of the iron core, right? So the primary is over here and the secondary is over here, and they're not touching, they're on separate sides. So it can be, arranged two different ways. So what happens is mutual induction. When the current in a coil is switched on or off or changed in a simple iron core transformer, right? So you've got like Optimus Prime and Megatron over here. A voltage is included in a neighboring coil, right? So voltage is coming in over here in the primary, and that is inducing, so it is creating a voltage, it is causing a voltage in the secondary. The effect, called mutual induction, is an example of electromagnetic induction, right? So this is electromagnetic induction. So what's happening over here basically is, right, when there's voltage in the primary coil, there is obviously current and there is a magnetic field, as we learned, right? So a wire carrying current has a magnetic field. When that magnetic field line, they travel, right, they are cut by this coil of wire over here. And we know that, when a magnetic field line is cut by a conductor, whether you're moving the magnet or you are moving the conductor, it doesn't matter, the motion is relative, right? When the magnetic field lines that are being generated by the electricity passing through this wire, those magnetic field lines are cut by these wires that are on the secondary coil. That causes a potential difference in the secondary coil. That's basically what's happening. Is that making sense?
Yes.
Are you sure?
100%.
100%? Okay,
Well, 90%.
that's still good. Okay, so obviously if you have any questions you can ask. So they're showing the setup over here, and they've got coil A and coil B. They have the same number of coils. So, right, the number of coils will make a difference. Just to let you know, if the secondary coil has more turns compared to the primary, then the potential difference in the secondary will be more. Why? Because the magnetic field that is produced by the primary is being cut more because there's more wire over here in the coil, and so the potential difference in the secondary coil is going to be more than the primary, right? And so that's change, it transform or changes the voltage either to a greater or smaller value. So if there are more turns of the coil in the secondary, it's going to increase the potential difference. If there are less turns in the secondary, then it will decrease the potential difference compared to the primary. So in this setup, it's the same, right? So what's happening is switching on the current in the primary over here sets up a magnetic field. So magnetic field set up by the current that is passing through the coil. And as its field lines grow outwards from the primary, so they're extending outwards, they cut the secondary, as I mentioned. The secondary coil is over here, and the magnetic field lines from the primary are moving across the secondary coil, and so they are being cut, and that's going to generate a potential difference in the secondary coil. A potential difference is induced in the secondary until the current in the primary reaches its steady value, right? So it's not going to keep increasing, it's going to come up to a certain value. When the current is switched off in the primary, the magnetic field dies away. Okay, so obviously the magnetic field will not stay if there's no current, so it's going to reduce. And again, it's moving away. And again, it is cutting the coil, and again, there's a potential difference, right? And we can imagine the field lines cutting the secondary as they collapse, again, inducing a potential difference in the secondary coil. Changing the prime, so this is the concept behind it, right? If you are providing current and you're switching it on and off. If you're attaching a rheostat, remember what a rheostat is?
I think I have a vivid memory for that.
You can guess, it doesn't matter, like, we're learning over here. What's a rheostat?
It's a stat that goes Rio.
Yes, but more accurately, it's a variable resistor. So you can vary the resistance of this setup.
Oh, okay.
So the more the resistance, the less the current passing through. The lesser the resistance, the more the current passing through.
So it can be adjustable, right?
That is what a variable resistor is,
Oh, okay. Okay.
right? So it says changing the primary current by quickly altering the rheostat has the same effect, right? So if you are increasing and decreasing the voltage, the resistance in this thing, that is increasing and decreasing the current passing through coil A, and that will affect the magnetic field it is producing, which is going to affect how much potential difference is being produced in coil B. And you connect that to a meter and you can take the reading off of that. Right? The induced potential difference is increased by having soft iron rods in the coils, or even better is by using coils wound on a complete iron ring, like they've done over here, I believe. More field lines then cut the secondary due to the magnetization of iron. So what happens is you are not only have the magnetic field of the current carrying conductor, the wire, but if you're passing the coil around an iron core, and right, that is going to cause the iron to become an electromagnet, and so the iron is going to have its own magnetic field, and so you're going to have a stronger magnetic field that's cutting coil B, and so you're going to have more potential difference being produced. Okay.
Okay.
Right. Now the transformer equation, right? We're talking about Autobots and Decepticons. So an alternating voltage applied to the primary induces a voltage in the secondary. That's what you learned in
Wait, actually,
what?
uh, never mind. Okay.
Okay. The value of the secondary voltage can be shown for a transformer in which all the field lines cut the secondary. So it is a ratio of the voltage of the primary over the voltage of the secondary, and it is related to the number of turns in the coil in the primary, like number of turns in the primary coil to the number of turns in the secondary coil, right? So the more the number of turns, the more the voltage, the lesser the number of turns, the lesser the voltage. That's basically how it works. Okay.
So you are saying that we can make an Optimus Prime out of this?
Not quite, but you can change the value of the voltage.
Okay.
So V stands for voltage, N stands for number of turns, right? P is for primary and S is for secondary. Now, right, this is applied in the kind of transformer you are making, right? A step up transformer, as the name implies, is where the secondary has a higher voltage than the primary. And that means that it has more turns in the coil compared to the primary. Right, so you can see that over here, the primary has less number of turns, the secondary has more number of turns in the coil. And so when the voltage goes from the primary to the secondary, the voltage will increase. And that is called a step up transformer. A step down transformer, the primary has more coils than the secondary, or the secondary has lesser coils than the primary, whichever way you want to say that. And so the primary will have more voltage, the secondary will have less voltage. Okay. So it depends on
Got it.
how you are setting up the transformer. Haram, are you following?
She's on her way to beat the Decepticon.
Yes.
Well, she said yes. Okay. Now we have, right, energy loss in a transformer, and then, yeah, the electrical power grid. So we're almost done. Energy losses in a transformer. So if the potential difference is stepped up, right, meaning the secondary has more voltage than the primary, and that means it has more coils. The current is stepped down. This must be so if we assume that all the electrical energy given to the primary appears in the secondary, right? So we're assuming that there's 100% efficiency. So that would mean power in the primary equals to power in the secondary. And so, right, P equals to VI or IV, however you want to say it. And so if there's 100% efficiency, this is what you get. What you can do is you can take a, flip that around, and you can do IS over IP equals to VP over VS. So this is just, this equation, right, for 100% efficiency, meaning that all the electrical energy you're supplying to the primary is 100% transferred to the secondary. And so it's basically power equals to power. And so, right, primary and secondary, you flip that around and you get, right, the current ratio of the current in the secondary over the primary versus a ratio of the voltage in the primary versus the secondary, right? So keep in mind that current is secondary over primary and voltage is primary over secondary. So for the ideal transformer, if the potential difference is doubled, right, the current is halved. In practice, it is more than half, right? So it becomes lesser, right? It's not halved, it becomes even smaller because of small energy losses in the transformer arising from the following causes. So there's resistance, right? So that causes loss. And when you're talking about energy back in unit 1, right, we know that the energy transfer is not 100%. So the windings of copper wire have some resistance and heat is produced. And large transformers like those over here, so you can see these huge guys over here, right, have to be oil cooled to prevent overheating. Then you've got eddy currents. So heat is lost, like energy is lost as heat. So it's not as efficient. Then eddy current, so the iron core is in the changing magnetic field of the primary coil, and currents called eddy currents are induced in it, which cause heating. So they're just mentioning that this happens. Again, what are eddy currents? Why are they produced? What are they doing? They're not giving any of those details. And so for the sake of your syllabus, that you just need to know, okay, fine, that's happening. These are reduced by using a laminated core made of sheets insulated from one another to have a high resistance. Okay, sure, if you say so. Leakage of field lines. So all the field lines produced, so the magnetic field lines produced by the primary may not cut the secondary, especially if the core has an air gap or is badly designed. Okay, so you can come back to this later and just take a look at, okay, fine. So there's resistance, there are eddy currents, there's leakage, and so the efficiency is lower. Any questions?
Nope.
Right. Now, finally, transmission of electrical power. So this is simple enough. A national grid is a network of cables mostly supported by pylons. So these big guys are called pylons that connect all the power stations in a country to consumers. So there's a power station, right? Wires going over pylons, finally coming to, the industries and towns and villages and farms and whatever. So the consumers. In the largest modern stations, electricity is generated at 25,000 volts or 25 kilovolts. And a step-up transformer is used to, increase that potential difference to travel over long distance, right? So you've got 25 kilovolts of, voltage, and there's a transformer, and it actually boosts it up to either 275 or 400 kilovolts. So that's so much more. And so you can imagine how much larger the secondary coil over here is as compared to the primary coil, right? To be sent over long distances. Later on, the potential difference is reduced by a substation transformer to, send it to local users. So there's another substation. So the 275 or the 400 is reduced to 132, right? At the National Control Center, engineers direct the flow of electricity and reroute it when breakdowns occur. This makes the supply more reliable and cuts cost by enabling smaller, less efficient stations to be shut down at off-peak periods, right? So you don't want every station to be working all the time. Advantages, why are they stepping it up so much, right? They need to step it down later because they're providing it to industry. So the heavy industries need 32, and so they're transformers, right? With the heavy industries, with the light industries, with the towns and villages, right? And so they provide the required voltage, as you can see over here. So transmitting voltage at a high value over the transmission lines, what's the advantage? The efficiency with which transformers step alternating potential differences up and down accounts for the use of AC rather than DC in power stations. Right? High voltages are used in the transmission of electric power so that smaller currents can be used to transfer energy, right? So what we just talked about over here, efficiency, high voltage means low current. Advantages of high voltage transmission include reducing the amount of thermal energy lost, right? So it increases the efficiency, allowing wires with small cross-sectional areas to be used, which are cheaper, easier to handle, and easier to handle than the thicker wires required to carry large currents. Remember that the thicker the wire, the lesser the resistance, if you recall, right?
Yes.
So if you have high voltage, that means you have low current, And so even though a thinner wire, and we're not talking about like the regular kind of thin wires we have, but still, right, compared to what you would require, the wires used on the transmission lines are thinner as compared to what you would need if the current was high. So they can use thinner wires because they're carrying less current at high voltage, right? So high potential differences require good insulation but are readily produced by AC generators. So they summarize that over here. The advantages are lower power loss and lower currents in cables, so thinner and cheaper cables can be used. And so this is an example of the national grid transmission system in Britain. Right?
Yes.
Finally, right, there's power loss in transmission cables. Power cables have resistance, obviously, and so electrical energy is transferred to thermal energy during the transmission of electricity from the power station to the user. The power loss of thermal energy in cables of resistance R is given P equals to I square R. Right? Remember, P equals to VI and V equals to IR. So P equals to IIR, which becomes I square R. So in order to reduce energy losses, the current in the cable should be kept low. And so that's a further explanation, right, of why high voltages are used to keep the current low. And so, right, you are losing less. And so you're increasing the efficiency. Okay.
Yes.
Are you sure?
Mm-hmm.
Obviously, right, go back, go through this again, process it, process it, sorry. And again, I admit that it's not a good explanation, right? In the book, but that's what we have. So a lot of these things are, especially in unit 4, are okay, fine, this is happening, just go along with it.
Okay.
And with that, we come to an end to unit 4. So I'll see you guys after a 10-minute break, and then we can at least kick off with unit 5.
So like you're gonna take a next session as well.
Yes, I am.
Okay.
All right.
Yeah.
See you guys in a while.
Okay, Allah Hafiz.
Allah.